Okay. So in this lecture we will continue our study of the low energy effective action of string theory, and today we're going to talk about a potential problem with this low energy effective action, namely the problem of anomalies. Okay. So I'm going to follow Kulczynski and introduce. Okay. I'm going to follow Kulczynski and introduce the notion of an anomaly through a two-dimensional example. Right. So suppose we had some currents. Let me stick a loop. So what am I doing? I'm giving you a sneak preview of something we will study in more detail rather soon when studying electronic theory in more detail. A sneak preview of something of the study of Kashmiri electrons. But I'm presenting to you the simplest case one we've encountered before, of a U1 current. Okay? So a Kashmiri algebra is the algebra of currents, of holomorphic and anti-holomorphic currents of dimension 1. Okay. The fact that they're dimension 1 tells you that their integral is dimension 0 and therefore conserve charge. Okay? So you can think of this current as being any conserved current in 2 dimensions, except that it's not just conserved, it's also holomorphic. Okay? Or any holomorphic, any current such that Jz is holomorphic and Jz bar is anti-holomorphic is obviously conserved, because del Z bar on Jz plus del Z Jz bar is 0, obviously. That's not the only way for current conservation to happen, but it often is the way that turns out to be implemented in conformity theory. For the obvious reasons, conformity theory meshes very nicely with holomorphism. Okay, so suppose we had a current such that when I write J, I mean Jz. When I write J bar, I mean J. I had a single holomorphic current of dimension 1, and I try to compute its OP. Okay. Now, there's a possibility of a singular piece that is k by z squared. This is the most singular possibility, at least consistent with unitarity. Because in a unitary conformity theory, no operator can have negative dimension. If you want a larger singularity, you have to have a negative dimension operator. That they don't exist. Okay, and then what could appear as we go on in this expansion, we'll deal with when we deal with Kashmiri algebras. So the only thing that I'm interested in is that this is the maximally singular structure. Okay, so if you have a theory of a holomorphic conserved current in 2 dimensions, the 2-part function, this is maximum singularity that can occur. And actually, just as in the study of the Virasoro algebra, you can show that unitarity forces this k to be non-zero and positive. Again, this is something we will see when we embark on our study of these guys. Okay, you remember that was true for the Virasoro algebra, right? It was just the idea was that there was some mod squared that was equal to this object, and if that mod square happened to be 0, then you get a trivial representation. Okay, it's a similar kind of thing here. So k's and k bars are in general not 0. Okay, now what we're going to do is to look at this U1 theory and to ask what is the effective action of the theory coupled to a background H field. Okay? So what I'm going to do is to take this theory and try to evaluate S of A, where A, mu, J mu, so I take the theory itself, whatever it is, fields, let's call them X, okay, plus J mu A. Like couple and do the one. This is equal to S. Okay? And my interest is in trying to evaluate this to quadratic order in A. So J is a function of X. J is a function of sigma, Z and Z bar, and A is also a function. A is a classical source.
So J is the current in the X area.
In the X area, yes. J's are functionals of the fields X, which are local at sigma. This is some abstract notation to say the fields of this conformity is there. Okay? So my interest is in trying to evaluate this S of A to quadratic order. Okay. Now that's very simple because well, I'm interested in evaluating the A dependence of this thing. That's very simple because it's you can obtain it by differentiating. See, suppose I'm interested in the quadratic dependence of this functional as function of A. I can take this object, differentiate it twice with respect to A, and then set A equals 0. Okay? So this double differentiation brings down 2 powers of this J field, yeah? And then the J correlators are evaluated in the theory with A equals 0. Okay? So the dependence of the action on A to quadratic order is completely determined by the 2-point functions of the J's. So the 2-point functions of the J's we know. Jz J0 is equal to K over Z squared. Jz bar, J0 bar is equal to K bar Z bar. Okay? Now, in this next 5-10 minutes, there's a particular qualitative point that I want to make. So I'm not going to focus on the numbers. 2 pi's and so on are all set to 1. Surprise, surprise. Okay? You'll find numbers, I think, I'm not even searched so carefully, but claim to be carefully worked out in functions. Okay? But yeah. So what is the value of this S or A of I think which is because of Z of A? Z of A. So Z of A, let me write down the answer and then we'll see if we understand it. Is equal to half d2z1 d2z2 or the exponent. Right. To quadratic order it doesn't matter, but Z of A is really the exponent. Yeah. So let's say e to the power minus Z of A. Well, I'm only evaluating things to quadratic order, so Z itself will turn out to be quadratic. And so it's 1 plus this. It's also the part that but really it's not. Okay, is d2z1, d2z2 times k over z1 to the whole thing squared times az bar of z1 z1 naught az bar of z2 z2 bar plus k bar z bar 1 2 the whole thing squared az of z1 z1 bar az bar sorry az of z2 z2 factors are also quite stable. For half when you differentiate two. Okay, so you may be wondering why is Z bar associated with Z1 to K Z1 to square, and that's because this J mu A mu, when written with both lower, is proportional to kz ez bar plus kz bar ez. Okay, so differentiating twice with respect to az bar produces the two-point function which is z. And vice versa. Okay, so after some factors that you could quibble about depending on your conventions plus x and z bars, some factors of 2, this is something clear. Okay? Good. Now, the question I'm going to ask is, let me take this quadratic effective action. Okay? Let me take this quadratic effective action and make a gauge transformation on the A's. Okay? A U1 gauge transformation on the A's. And ask if this effective action, this Z of A, changes under this gauge transformation. Now, we know that it should not. We know that it should not because the gauge transformation nothing should change under the gauge transformation. Or more prosaically, since J in the actual theory was just some conserved current, we should be able to take that just from conservation. And that's clear, right? Because suppose I change A mu by del mu of theta, then I integrate by parts. Del mu will get J mu and give me 0 because J is conserved. So as long as my current is truly conserved, as long as the current to which I am coupling this A is truly conserved, then under a gauge transformation this effective action should not. This is clear. Is that clear? Excellent. So I'm going to experimentally check whether this is true. Okay. So let me start. Let's look at how this thing changes under gauge transformation. You'll find this analysis quite similar to stuff we did with central charges. But okay. So let's look at this term for instance. Az bar, Az bar. So gauge transformation can act in one or two places. Let's say it acts in this guy. Then it changes by this thing by del z bar. Okay. Now this is z1. This is z2. These are different variables. So I can take this del z bar, which is acting on the one variable, and integrate by parts. It doesn't act on this function named z2. It acts on this side. Okay? And then we use this this fact that we remember very well, that del z bar of z, 1 over z, is the delta. Right? Because that's the same thing as del squared on log 1z. Log of 1z is the Green's function for the Laplacian operator. Right? So del z bar on 1 over z is the delta function. So again, after some factors of 2 and some minus signs, which I get right by doing a Polchinski, this guy is going to be what? It's going to be the z derivative of the delta. Because if this was just 1 over z, by integrating by parts, I would have got z derivative delta function. I would have got just the delta function. But this is 1 over z squared. 1 over z squared is del z of 1 over z. So I get del z of the delta function. Okay? So now let me write out the answer and then let's see if we believe it. We get delta z is equal to minus pi. Minus pi is because we get pi times delta function, something like that. Okay, the integral d to z. Lambda a, that's Polchinski's notation for the gauge transformation parameter. Z bar into k times del z dz minus plus k bar times del z bar okay. So let's see if we understand this. This guy transformed by del z bar of lambda, integrating by parts here, make this del z derivative of the delta function. Okay, and then that that derivative of the delta function will be transferred to this variable, and then the delta function did its magic, changing an integral over z1 and z2 to an integral over secant z. Okay, so you can easily relate to the z derivative of a z bar multiplied with the Gaussian transformation parameter and the k which came from.
The leading case lambda won't have any.
What? The leading case lambda won't have any? Sorry. Yes, the leading case lambda. Thank you. Yes, but just see what's a more gestural thing to make a point in leading case. Okay, and then you repeat the whole exercise here. Okay, excellent. So the first thing we see is that this object here looks like it transforms under H transformation. This thing is not zero. This thing is not zero. But something simple is happening. You see, why it's not zero? It's changed from being a non-local expression to a local expression. You see, the expression for z itself involved a at one point, a at another, convoluted by a non-local, whatever you call it, spherical functions, some non-local propagator going between the two. So while z itself was a non-local object, the variation of z, while not zero, is now local. Now, you might think at this point that, well, whether local or non-local, variation of z is not zero, that means my current is not really conserved. And that is, in some strict sense, true. But the correct question, the correct question that you should ask is it possible for me to define my quantum theory in a way to make this current? What does that question mean? You see, that question means, is it possible, you see, when you've got a quantum theory, as you know, in order to define it, you need to cut it off at some high energies and work with the Lagrangian at that scale. So the question you could ask is it possible for me to add a counter term to the Lagrangian at this high cutoff scale so that the classical variation of that, so that the add a counter term which itself is not gauging variant. Okay? But chosen so that the classical variation of that counter term will cancel the variation of this formula. If this is possible, this amounts to redefining your current. Okay, with some small counter term. And if this is possible, you can choose the definition of your theory to include this counter term. And so to have a conserved, and your theory to actually have a conserved current. Okay? So let's see in this case whether that's possible. So let's say that in my z array, I just add by hand a piece that is that prime of A is z of A plus alpha times the integral Az Ez. Then you put minus phi alpha. So alpha some unknown. Okay? Now, let me look at the variation of this z. Variation of z of A. What is the variation of z prime? Well, the variation of z prime is very simple. This guy changes like del z lambda. This guy changes like del z bar. Okay? So, the next change is exactly of this form. You take this del z here and this del z bar. There is exactly of this form if and only if k is equal to k bar. You see, this quantity here is the change under gauge transformation of pi integral d to z is times k, if k equals k bar. You see that? But if k is not equal to k bar, there is no local quantity you can write down whose variation under gauge transformation is equal to, and so it cancels. Is this clear? Okay? So, if k was equal to k bar, we could change our definition of z prime A. This would be automatically effected if we chose counter terms so as to make the theory generic. Okay? To choose the counter terms so as to make it generic. In that way, and that amounts to changing the definition of the current in such a way that the OP, in addition to the 1 over z square piece, has a delta function. Right? That's what you get by varying this delta function contribution. Okay? And, something I should have emphasized when we were studying conformity theory is that all these relations that we got many times, all these OPs that we produced were only supposed to be trusted at distinct points. When the 2 points bang on top of each other, there could have been contact terms, could have been delta function like contact terms, which need not correct. And the point is that what we are observing here is that it's possible to correct this OP relationship with delta function like contact terms. Okay? Which would be contact term between Jz and Jz bar. So as to make the current conserved, or so as to make the effective action be right, if k is equal to k bar, but not otherwise. Is this clear? Okay? So this is the prototypical situation of okay. So what do we try? We started on trying to investigate whether a current that appeared classically to be conserved, or operators away del z of holomorphic, whether it was really conserved, whether it was truly conserved in all correlation functions. And we found that if k was equal to k bar, we could choose our definitions of things appropriately so that this is true. But if k was not equal to k bar, we could not. Okay? The second situation is referred to as the situation in which a current is referred to as being anomalous. Okay? It's a situation where you expect to have a conserved current. Looks like classically but a conserved current. Okay? But there's no way of defining the quantum theory so as to preserve that current. Keep that current true. Okay. This, like everything in Brzezinski's book, it's just such a beautiful one-page demonstration of an important but subtle idea. The important but subtle idea is that quantum calculations often reveal that a current is not conserved. But that's not the end of the story. You have to search for ways of changing your definition of the current to try to make it conserved. Your job is not to give up at the first sign of trouble, but to try to make things work. However, there are some situations in which you can't complete that job. The structure is incompatible with things working. And that's the situation in which a current is said to be anomalous. Right? In this case, k not equal to k bar would be a gauge anomaly. You remember we saw something similar for diffeomorphisms. C was not equal to C bar. It was not possibly consistent to couple it in a coordinated manner this clearly to a background. It was a different anomaly. We had a discussion of that in slightly different words for a year ago, 2 years ago, it was. But it's essentially the same discussion. You may want to go back to that and look at it. Okay, great. So this was our brief introduction to the idea of an anomaly. Okay? Any questions or comments? Okay, great. Now that we've reminded ourselves what anomalies are, what the issues are with anomalies, let's continue. Let's continue by describing something else that's by describing something else. As we have seen, an anomaly can be worded as reflecting the lack of the transformation of the effective action under a gauge transformation. Okay? So suppose I take Z and I vary with the gauge transformation lambda 1. Okay? And I get some okay, and I find some, let's call it V lambda 1. But because V lambda 1 is the variation of a well-defined object under a gauge transformation, it follows, of course, immediately, well, it's immediately obvious, the del lambda 2 del lambda 1 minus del lambda 1 del lambda 2 acting on Z is equal to V of lambda 1 lambda 2 acting on it. This must be true. Right? Just because the property of gauge transformations, this combined operation of gauge transformations is this operation, this gauge transformation. Now, what we're going to do is to try to write down the possible forms of variations of effective actions under gauge transformations. Now, abstractly, you might think that V of lambda 1 okay, was just any function of lambda 1 in it. But if you follow it that way, this condition here gives you a consistency requirement of V lambda 1. It's the requirement of del lambda 2 of V lambda 1 minus del lambda 1 of V lambda 2 is equal to V of lambda 1. This is what's called the West-Zumino consistency condition. It's an obvious statement, but it's obvious only if you think of the problem structure. You get enmeshed in Feynman diagrams, it's very easy to forget them. The structure is just okay. Now, the question we're going to ask is how can you solve this West-Zumino consistency? Now, clearly, one way to solve it is to have if V lambda was equal to delta lambda of something. Because the variation, I should have said something. Sorry. Let me back up. Something else that I should have pointed to in the formulae that we have on the board, but we'll ask you to point to the formulas you have in your notes, is that something we remarked on was that, see, even in the situation where the current was anomalous, although the effective action itself was non-local, the variation under the gauge transformation is local. This is a usual story. Okay? This is a usual story because anomalies typically are symmetries of of classical action that cannot be preserved by regularization. Since regularization is an arbitrarily high energy phenomenon, okay, all lack of variation of lack of gauge invariance under normal gauge transformations must be effectively arbitrarily high energy phenomena, and therefore encodable by in a local. Okay? So it's a very general property that while the effective action itself is necessary, generally a highly non-local function of all the fields, the variation of that effective action, whether in a situation where it's really anomalous or not, is a local. Okay, we saw that explicitly in the previous example, but it's a completely changed thing. Okay. Now, we are very happy to add local counterterms to our quantum field theory to cancel the quantums. We're not going to allow ourselves to add non-local counterterms to the cancel. If you allow yourself to add non-local counterterms, you can cancel anything. You can set Z of A equals 0 or 1. Right? Because whatever Z of A is, you subtract on Z of A. But that's not allowed. And the reason it's not allowed is that only local actions that involve no more than, in some way of looking at it, single derivatives on individual fields, at least single time derivatives on individual fields, are manifestly equivalent to Hamiltonian formulations of quantum theory, and therefore are manifestly causal immunity. If you get into the game of adding non-local objects to your Lagrangian at some high energy scale, you can formally do anything, but you lose all the good properties. You're not guaranteed to keep any of the good properties of a quantum field theory. In particular, unitarity is very slippery. Could easily fail. Okay, so so it was very important that we could cancel, in the case where the situation, the anomaly was really not there, that we could cancel the anomalous variation by the addition of a local counter. And with that to a counter without many derivatives acting on individual fields. Good. So, now we come back to this situation. So, this V here was variation of Z under gauge transformation, and this object is a local expression. Okay. Now, of course, one way to satisfy this condition, this Westermanian consistency condition, would be to have V lambda being delta lambda of zeta, where zeta is some other local expression. The Westermanian condition is automatically satisfied if you implement things correctly. But what we're trying to do is to understand what kind of local expressions can satisfy. So one obvious kind of local expression that can satisfy it is if V lambda is delta lambda of zeta, where zeta is another local. But this is precisely the situation in which there's no real anomaly. Because you subtract zeta from your action, and now the theory has no anomaly. That's what we did when K was equal to K. Is this clear? Okay. So, while this is an easy solution to this equation, it's not a very interesting solution. However, there is another clever formal solution to this equation called the solution from the descent relation, something like that, which we now review. And we use the notation for all our discussion. And this formal solution goes as follows. It goes like this. See, suppose I have, okay, suppose I'm working in d dimensions. And I have a d plus 1 form such that the variation of I d plus 1 with respect to lambda is equal to v, is equal to d of v lambda. V is a d form. Okay? It's some object that can be equivalent to the space time. Okay? formally consider a d plus 1 form. Okay? That whose variation under gauge transformations is d of v lambda. Okay. No, there's no connection. D is just the space time. Is D in space time, extended dimensional space time. Okay. Now, suppose I could take space time and regard it as the boundary of a D plus 1 dimension. This is true in flat space, for instance, if you go back to pi infinity, because then flat space is a sphere, it can be filled in by a solid ball. Okay, so then in that situation, V lambda integral of I d plus 1 over the ball, the space whose boundary is the actual space. The lambda variation of this is equal to integral of d v lambda over the ball. So that, by Stokes' theorem, is integral of v lambda over space. Integral of v lambda over space time is what we wanted, is what we obtained from our calculation on varying the effective action under the gauge transformation. You see, so if there exists an object like this, such that delta lambda of I d plus 1 is equal to d times d of v lambda, then you see that there is a clever formal way. Then you see that there is a clever formal way of having our gauge transformation, having our v lambda manifestly satisfy the Western consistency condition. Because now this is the variation of something. Okay? Without it necessarily being that the anomaly is actually not there. That the anomaly can be removed by a local current. Is this clear? Now, of course, this situation here, this is going to, anyway, let's switch on. So, this situation here can be, includes the situation in which the anomaly can be removed by local current. Okay? And that is a particular case when I d plus 1 is equal to d of some I. Okay? In that case, the d's sort of cancel out in this relationship, and we've got delta of I d is equal to v lambda, in which case the anomaly can just be removed by a local commutative recondition. So, we want to look at situations like this because it's also basically consistently a condition. However, not to be in the situation when this is true. Okay? Now, is there a way of doing that? And there is a clever way of doing this. Okay? And the clever way is to insist that I d plus 1, d of I d plus 1 is equal to I d plus 2. You see, suppose we were in the situation so that I d plus 1 was d of something, the d of that would be 0. So, if d of I d plus 1 is non-trivial, then it guarantees that we're not in the trivial situation. Okay? So, this is essentially the idea of, I don't know whoever invented this. Now, I'll give you a very rough introduction to what is actually a rather mathematical subject. But I've tried to pull out what I think is the essence of the story. And left many proofs outside. But the the claim is that at least with making a lot of reasonable assumptions, the most general local counter term, the most general local anomaly expression, which cannot be removed by a local counter term. Okay? Is parameterized by a gauge invariant polynomial in of forms, gauge invariant polynomial of gauge invariant d plus 2 form, local gauge invariant d plus 2 form, and the relationship between this d plus 2 form and the d form goes like this: d I d plus 2 is equal to d of I d plus 1, and delta of I d plus 1 is equal to d of d plus 2. So we're going to take this route of parameterizing expressions that can appear inside anomalies. Okay? The route we're going to take is to write down I d plus 2, and then the actual anomaly expression we get by solving these equations. By finding I d plus 1 such that b of I d plus 1 is d plus 2, and then finding b of lambda such that delta of I d plus 1 is d of b of lambda. Okay. Now, okay. If you get a slightly more complete discussion of this subject, we'll look at Greenshaw's in chapter 13. To get a properly complete treatment of the subject, look up the references of Greenshaw's. Okay. Mainly now said to motivate. Basically, the notation. Okay, the last thing I want to say is about this kind of stuff is the following. Suppose we were dealing with gauge theory. Then, you're familiar with the fact that let me do it for an let me. Yeah, okay. Are you familiar with the fact that f wedge f, that trace of f wedge f is delta of the transform? D of the transform. Yeah. So in these dimensions, this is a statement that most of us have encountered before. Okay? There is a generalization of this statement to arbitrary dimensions and to arbitrarily complicated expressions. Which you will find somewhere. Yeah, which you will find in equation 13.3.35 of Greenshaw's. Okay. In general, trace f to the power n, and we will often be interested only in even powers of n. Because trace of one power is 0. By trace, by the way, I mean wedge product. Just because of the wedges. Suppose you have wedge f, and then you circulate the wedge around it. What? These are all two forms. Oh, you're saying that should be. Okay. let me see. Well. Yeah, you're right. Sorry, what am I going to say?
In fact, I think we need the all.
Well, that's just.
With the five-dimensional judgments forms from FQ.
Okay, if it turns out I need only even I'll think about it. At the moment, that's okay. Is D of some expression which we'll generalize and call the German science expression? This can always be written that for every m, as you will find in the expression we use. There's an explicit construction. So I think hang on for a minute, let me check what's the point.
I think the whole form will always be even because f is even and we take any number. So that
Yeah, that's okay. Thank you.
probably not.
Thank you. That's the whole form is always. Yeah, that's always. Thank you. Yes, because it's correct. Absolutely. Okay, good. So for every m, it's possible to write down some local expression in terms of a's that generalizes the Chern-Simons expression in 3 dimensions, so that this is true. Okay, and because this is true, given any gauge-invariant polynomials of x, something that involves trace f to the power 2, f to the power trace f cubed, and so on. Okay, you can always write this object as d of something. You could write it in many different ways. For instance, this is d of this Chern-Simons form times this object, using the fact that df is 0. Okay, so d of the Chern-Simons form gives us the net square, and then d of this, which is not the same. Or you can do this Chern-Simons form this. Okay, so basically then, this equation is easy to solve when you write I b plus 2 as a polynomial of traces of gauge-invariant quantities. And then it's also possible to solve this equation in that situation. Rich-Watson gives details of how you can do it explicitly in certain cases. Okay, so eventually, what is the upshot of all of this? The upshot of all of this is that we are going to parameterize possible terms that can appear in anomalies. Okay, we're going to parameterize possible terms that can appear in anomalies by traces of f's and corresponding curvature kind of that was one of the gravitational anomalies. But since we're going to run a 10-dimensional theory, we'll write down 12 forms that parameterize this. Okay, ID plus 2. And then the anomalies that we get are obtained implicitly by these expressions. Obtained implicitly from this parameterization by these expressions. Okay? Okay, is this clear? Okay. So now what we're going to try to do is to write down, is to try to review the calculations that we have done, trying to compute whether the various consistent string theories are anomalous. Now, as we said, anomalies arise because of difficulty in regulating a theory. Now, whenever you can take a theory and regulate it in a way that preserves the symmetries, the theory can't be anomalous. And in any situation in which the objects in your theory are not chiral, for instance, the fermions in your theory are symmetric under parity, you can always regulate the theory by writing down a Pauli-Vidas condition, for instance. Okay? So, anomalies are associated with asymmetry under parity. Now, which of the string theories that we looked at have fields that are asymmetric under parity? Not type 2A theory. That's nice and non-time. The type 2B theory is a theory which is sky. So, double the number of left moving supersymmetries, no right moving. Double the number of left moving gravities, no right moving gravities. Okay? So, the first theory that we should be worried about is type 2B theory. So let's first discuss that. Okay. In order to discuss this, I'm now going to quote the results of some calculations. Okay, something else I should have said that you're probably aware of is that anomalies in 4 dimensions are computed by computing triangle diagrams. One way of understanding why this is true is that in 4 dimensions we need anomalies are parameterized by a 6 form, as we just see. Okay? And the smallest number of gauge bosons in a 6 form is 3. It's F. Okay? So, it's not. Well, all the information the anomaly is computed is contained in the triangle diagram. In the second way, in 10 dimensions, all information in the anomaly is contained in the hexagon diagram. Because you have 12 forms, and the smallest number of gauge bosons involved in an interaction involving 12 forms is 6. Okay? So there are some calculations, one loop hexagon diagrams that characterize anomalies in 10 dimensions. Okay? And people have painstakingly sat and computed all these hexagon diagrams. Now, what I'm going to do, write down is the anomaly polynomial obtained from the hexagon diagrams obtained by the exchange of various kinds of vector fields. Okay? So we can write there's a hexagon diagram here. And at these vertices you could insert currents, any kinds of currents you're interested in. In type 2B theory or in string theory in general, we will be interested only in 2 kinds of currents. The first current is some non-abelian gauge field. This will be relevant to type 1 theory of the encoding string. And the second current is the current of the gravity, currents. Calculations are all done. You just exchange massless particles. Yeah, only mass. You see, massive particles always have massive particles, since they have a mass, can be continuously taken to the mass can be taken to infinity. So it doesn't matter. The massive particles can be regulated. It's only the massless particles, because of chiral nature, that potentially cannot be only their contributions can potentially not be regulated. It's only massless particles that are chiral massless. Massless particles with content such that they can't be consistently given mass. That could contribute. Yeah. So, right. So anomalies have this feature that while they're associated with divergences, in the sense of being a property of not being able to regulate the theory, they're also in some sense associated with the interact, because they come purely from massless particles. So they have this very strange dual role, which makes them very important. Because they are associated with the infrared, you can calculate them even if you don't know what the full thing is. So only the massless part of the spectrum is okay, good. So now what we are going to, so we will be interested in the insertions of either non-abelian gauge currents here or curvature currents, stress tensors at those points. Okay, and okay, so now let me write down some relations, and I'll tell you what they mean. They're quite horrible. They're horrible enough to write down. Imagine how horrible they must be when they complete. Okay. I'll just run one of these actually. Just say that. But just to give you a sense of what kind of number. This whole thing is multiplied by the derivation. Okay. So what is this? Suppose we have a chiral spinner in the theory, fermion. The 8 there refers to the fact that it's a spinner. It transforms the 8-dimensional representation of SP. Okay? This spinner is coupled to gravity like spinners. And is coupled to a non-abelian gauge theory, whose field strength is F, in some particular representation of that non-abelian. Then the anomaly polynomial associated with interchanging this 8 line, encompassing the effects of all kinds of anomalies. Pure gauge anomalies, pure gravity anomalies, or mixed gauge and gravity anomalies, is given by this.
Only the contribution of the parents.
This is only the contribution.
So, how many polynomials are there actually? How many coefficients do you have?
Yeah. So you're asking if there are accidental zeros. So we certainly have to compute all these coefficients.
No, I mean, usually there are only you can classically for the
IB plus 2s are allowed.
and there are a certain number of them, and we just have to compute some coefficients.
Yes. Yes.
Like the same diagram, what I'm saying is that like the same diagram usually contributes to a lot of. I mean, you can compute one diagram and that determines the coefficient of a lot of.
Well, you mean one?
Yeah.
Different numbers of insertion, different insertions which stress tests and which current.
if you compute one of the diagrams, then
this is the diagram to be computed. By one of the diagrams, you mean
with some insertion.
with some insertions. Yes.
Then I would imagine that you determine more than one of these coefficients.
Well, no, I think you're right. I think that one of these diagrams with arbitrary sort of gauge structures here would determine. You see, suppose you've got a diagram with all 6 gauge bosons. Yeah, why did we have? It's nothing more. Okay, suppose we have a diagram with all 6 gravitons. I think that will determine this, and this. Because these are the things that participate in the 6 gravitons.
So for the relative coefficients, you can't get anything with it.
Well, the relative coefficients from. Oh, you mean some consistency determines that?
Yes.
Is that right? I don't know. What kind of? I thought these were all. I mean, for instance, I think the relative coefficient will depend on what's propagating. You can check that. Let's see. No, you seem to be right. All the relative coefficients are the same for both the guys. Yeah. So apparently that's.
Usually they write down some expanded just have to determine the coefficient.
Okay, so you're saying that all of these, for instance, will be. Yeah. So I think that that a given diagram will determine all the terms with the same species of fields participating. Here you could put in some number of stress tensors, some number of gauge fields. And all terms with that number of stress tensors and that number of R's and that number of F's could be determined by that diagram. But it was not so clear to me that. It wasn't so. It's probably true since it's probably true since you're saying it, and since it's only true from the results. Okay. Apparently, it's true that these coefficients don't determine on what's propagating in here. I don't know why that is. It's a good point. I don't know.
No, usually some over.
No, but I'm going to quote you results of individual things propagating.
Okay.
And they all have the same relative ratios.
Okay.
So it's probably true that that's fixed by some universality, right? I don't know what that is. Yeah, so there's more to say about the structure than I'm telling you.
Usually you have some characteristic class if you expand
That's right.
From negative.
That's right. So like this e to the power f. Yeah.
No, multiplied by something which contains R.
Which contains R,
Right.
right?
R should be the.
Right. Okay, good. Yeah, this sounds familiar. There's some story there. I don't know. Yeah, so certainly these relative coefficients. So you're saying it's like, I know what you mean. Like this A root genus. There's some story behind it. So this probably have to do less work to determine than all the individual numbers.
But how many are there? Okay, how many variables? Okay.
You mean how many things could have had different ratios? Well,
is it just two coefficients?
no, I think each of these is totally distinct. There's a number of so this is a diagram. This, and this are 4 different kinds of diagrams. That's like 4 different nature of insertion. The others, unfortunately, don't talk to gauge field, so it's all proportional things. Okay. N here is the trace of identity in this representation. Okay, it's the size of the representation. The dimensionality of the representation of the gauge group in which the current universe propagates, And it's clear that a factor of n should appear here because as far as gravity is concerned, what each component under the gauge group behaves identically. So it's just a factor. Okay, and fine. So this is what we get from the chiral guys, from the 8s. Then we have I56 is equal to no. Sorry, these ratios are not the same. Right? They take that. Sorry. Minus 495 by 725 760 trace of 26 by minus 225 trace of 2 to the 4 trace of 2 square by the same number 55960 minus 63 1270 trace of 2 square. So sorry, I said that wrong. These numbers are not the same. They look the same because they're the same denominator, so that's what in my hand. They have different numerators. When this was all n, here is 495, 225, 60. So there isn't a mystery basically. Okay, and in addition to all of these, there's also the self-dual region. The self-dual 5-form piece. Because it's self-dual, that is also chiral object. Okay, so it also contributes to the anomaly. So the self-dual 5-form field strength also has one contribution, and it's okay. It's this object 992 is R26 by the same denominator minus 448 trace R2 to the 4 trace R2 square by the same denominator minus 128 blah 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 by the same denominator. Alright, these are all the basic ingredients we're going to need to discuss in our video. Look at the numbers, by the way. Okay, the numbers are enormous. Even the numbers, once you factor out collective things, are quite large. 495 to 2563. So easy cancellation are going to happen. Okay. So now let's start looking. At type 2B theory. So type 2B theory has no non-Arrhenian gauge fields. So it's only this gravitation. You know here? There's no non-Arrhenian gauge fields. It has 2 fermions in the 8. Okay, so let me write it down.
This is just a trace evaluated with
Trace of what?
I mean, what I'm saying is that maybe the relative coefficients are just. I mean, there's a way of writing all these 3 things, 3 contributions as trace evaluated over different representations of trace of whatever.
Maybe there's a way of making it look more uniform. I don't know. Yes. 63 is an odd number. Yes, maybe. Yeah, could be. Okay, so fine. So in type 2B, we've got minus 2 times I8 plus 2 times I56 plus I17. minus 2 times I8. Right? Right sign of I8 956 minus. So is I56. 56 gravity. Right. You see, the chirality of the 8 and the 56 are opposite. You see, how do you get the 8? You get what you have is some object that transforms with one index as a vector, the other index is scalar. There are 8 vectors, so that's 8, and 8 scalar components, so that's 64. That 64 decomposes into the 56 plus 8. How does that decomposition happen? How do you get a spinner? Well, the Radita spinner part of it is just by throwing away 8. Right? But the spinner itself is obtained by contracting with Raman. And that looks like that. Okay? So the 8 and the 56 are in opposite chiralities. And therefore contribute oppositely to 0. Okay? You have to be careful about the reference sign of this, but be careful that's this. Okay. And now all you have to do is add. And you add, and what do you find? Let's see. We're supposed to flip this sign. So, well, n here is just 1. Okay? We're supposed to flip this sign. So we get 496 into 2. So that's 992. This is with the minus sign. That's with the positive sign. So that cancels. Is this clear? 1 with the minus sign, so minus 496 into 2. Because each of these appears with. Why do each of these appear with 2 by? Step 2. 2 chirals, 2 gravity equals 2 chiral spins. But one side, self-repeating gravity. This is it. Okay? So that's that. Let's look at the next guy. This also appears with a 1, but it appears with the minus sign. We'll flip the sign, so it's plus 1. This guy appears with 225, so that's 224. Multiplied by 2, 448. Boom. Okay? And this guy appears with a 1. We flip the sign to minus 1, minus 64, plus 128. Boom. Okay? So the master's content of type 2B theory automatically cancels out. Okay? The numbers here are sufficiently big so as to give you the feeling that this wouldn't happen by coincidence. Which one? This one? See, this coefficient is 1 here. It appears here with minus sign. Minus 1. I multiply by 2. Minus 1, minus 496. That's 495. Okay. And minus 1. So 496. Multiply by 2. That's 992. Okay? So type 2B theory has a very simple story. We normally look at it. That's very nice. There's no non-linear field. So in this theory, the representation is trivial. Okay, so there's only the gravitational phenomenon. And all this. Okay, quickly, I'll just zoom in and come and take the camera. So let's see. Okay, so now you might think think that, well, we knew this had to happen because string theory is consistent, we've taken great long to make it consistent, blah, 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 blah. So the low energy effective theory of variable consistent. All that's very well, but it's very nice to see it actually work. Because in the end, this low energy analysis is consistency condition, independent of the details of how you completed your theory. So it's nice to see that some orthogonal way of looking at it makes it work. Okay. Now, what about type 1 theory? Okay. So let's look at type 1 theory. Type 1 is the heterotic, type 1 and heterotic SO30. But type 2A, by the way, there's nothing to see. So everything's chiral and not chiral. So the contribution of one chirality cancels is contributed to the other field by field. So it's obviously. What about type 1 theory? Type 1 theory is sort of interesting. Type 1 theory SO32 and heterotic SO32 have the same mass and spin contents, the same calculation. Type 1 theory is sort of interesting. When you look at it first, you say it can't work. Why can't it work? It can't work because the only field that is charged under F2 is the 8. Right? So type 1 theory has a gravitino, which has, for instance, a gravitino that's charged, that of course uncharged under the gauge rule. But the only chiral field that is charged under the non-immediate gauge rule is the chiralino, the 8. Remember the field content of type 1 theory? Somebody remind me of the field content of type 1 theory. There's the gauge boson and its superpartner, which is a chiral fermion. Both of the atoms. Okay? And then in addition you have some of the fields of type 2B theory, those that are not projectile. Okay? And these fields include the graviton, the dilaton, but not BB2. Include the hat mu, the two-form RR field, and its dual. Basically nothing else. B you will find this. Okay? So that's the field content of type 1 theory. And then all the fermions associated. Right. Okay? So that theory, in particular, the only time that's charged under the gauge field is this object. And now you look at the anomalies. There was this magnificent cancellation between various terms here, because all three kinds of fields contributed to the gravitation. And that's fine, that may or may not automatically work. But this term, let's say this term, how do they ever cancel? When do they have to cancel again? It's only one field, it has now 0 component. Seems to stop resolve. Okay? So this was a huge puzzle in string theory. It was something that, in my understanding, was used by people to think string theory was complex. In the early 1980s, there was a reason string theory was not taken seriously by most people. So you get a theory which, in the end, can't be consistent because it's anomalous. So I don't know what blah 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 is done, it's very complicated. But I know in the end it can't be consistent, so why should I look at it? That's the attitude that many people would reasonably have. However, the attitude was too glib. I said, now we're trying to take it. I'll give you the main idea now, we have to go. I'll give you the main idea immediately, and then we look at the details. The main idea goes as follows. Well, you see, let's look. The main idea is this. All of this Wessuming of blah blah, all of this parametrization of these terms as terms that give you genuine anomalies that can't be removed by a local counter term. Assume that your local counter term is built out of F and R. as we have seen in supergravity, certainly in string theory, there's another term whose variation under gauge transformations is volatile, and that's V. You remember that V, the two form, yeah, had a variation under the ordinary field, strength, such that delta V was equal to lambda times trace lambda. Trace lambda and delta. We're finished with one.
No, you can continue.
Okay.
That's a
Okay. So,
it's going to go for longer time?
no, just 5 minutes. No, it's fine. 5 minutes. It'll give us a little more brief. Okay. So delta V is trace lambda times F. Okay. So now, suppose you had a term in your a local counter term. Okay, suppose you had a local counter term in your vector action that took the form B times trace F to the 4. Since B itself varies under transformations, okay, under gauge transformation, you could produce a delta, so V lambda, of the form trace lambda F times F to the 4. Now this, as I'll show you, I suppose, in the is obtained from descent from something like trace X squared. Trace. Okay, you can basically check that by seeing that, well, it's easy to see. Basically, the fact that this is D of the usual Chern-Simons form times trace F to the 4. And the gauge variation of the usual Chern-Simons form, that's lambda times F. Okay, so but we'll see all this in more detail next class. So anyway, so this kind of term that from a normally polynomial analysis looks like an independent polynomial, one that gives rise to a counter term, one that gives rise to an expression that can't be cancelled by a local counter term, is not really an expression that can't be cancelled by. Okay? It can be cancelled by a local counter term in the supergravity theory of string theory, because there are other fields other than F and R that change under gauge transformations. That change under these gauge transformations. Okay? So the traditional anomaly analysis assumes that there are no fields transforming in this funny way, in the kind of funny way that B does transform. Okay? When you put that information in, many of these terms that look like from traditional assumptions cannot be the gauge variation that they give rise to by traditional assumptions cannot be cancelled by any local counter, as we've seen. Okay? Now can be. For instance, if there was a term like trace X squared trace, well, this could have been hard. So this term, okay, could have been traced out to the X squared. This term, by this mechanism, can be cancelled by such a counter. Okay? Now, as we're going to see, in more detail in the next class, this systematically thinking this story through, okay, allows us to potentially actually cancel all the anomalies in type 1 theory. But if and only if the gauge group of the gauge theory is either SO32. Okay, let's say the heterotic theory. In the heterotic theory, well, in the theory of the speedy content, if and only if the gauge group of this theory is either SO32, E8 cross E8, or U1 to the power 496. You see, this will appear in number. We'll see this in detail. The rank of the gauge group will be important in determining this aim. Okay, so that's what happens with gravitation, at least apart from the we'll see this in more detail. But the specific nature of the gauge group will be even more important for the following reason. Now you see, I've told you about this kind of mechanism. But this kind of mechanism only seems to apply to those anomaly polynomials that have factorized form. At least 2 traces. Because the B itself will produce 1 trace, and there'll be some other trace. So it looks like things that have a factorized form can be eliminated. That's a need for use. However, what you have to remember is that this trace is a trace in the representation in which this 8 appears. And this 8 is the chiral inner, which is the adjoint representation. Okay? All the expressions that we've written down here are in the vector representation. So, in order to correctly see whether such things can or cannot be cancelled by this mechanism, we have to take these traces and rewrite them as traces in the fundamental representation. And precisely for SO32 and E8 cross E8, well, actually even E8, but then the rank condition is right, E8 cross E8. Precisely for these gauge groups, it turns out that the expressions for this object in the adjoint representation is written purely in terms of factorized forms and written in terms of fundamental traces of the fundamental. So all these will work out. Okay? But all these expressions here are of the form that can be cancelled by local counter terms from these particular cases. By any other gauge group it can't. And this is sort of quite nice, because we found from different sounding considerations in string theory the same results. Like SO32 or E8. Okay. Now there are 2 other things that in this general overview, we'll look at a few more details next time before moving on to describing the nature of superstring interactions. But we will look at just 1 or 2 other things in this overview. The first thing to say about this is that from the point of view of effective field theory, all we keep talking about is, can you add an effective local counter term to cancel it? However, in string theory, there are no UV divergences. There's no about the string state, everything is soft. There's no ambiguity in what terms in your vector actually match. The theory is completely clear and precise. So, while this effective field theory mechanism gives you a suggestion for how things might work, in string theory, all these counter terms that are required to cancel these anomalies must actually be there, and their presence should be verifiable by direct computation. This is indeed true. And in fact, it's the historical procedure by which this anomaly cancellation mechanism was discovered. Green and Schwartz undertook a very detailed analysis of the string 1 loop diagram. Because, as far as they could see, string theory was totally fine, yet the field theory content seemed to be saying anomalous. You could see no sign of this anomaly in string theory. How could that be? They undertook a very detailed analysis of the string 1 loop diagram and realized that there were these additional counter terms from string theory, and then realized, aha, this is how it works in vector. Okay? So in string theory, it's better than saying these are of the form that can be cancelled by local counter terms. String theory actually has these local counter terms that cancels. Okay, that's the first thing to say. The second thing to say is okay, then the second thing, last thing I'm going to say this lecture is, you know, there were all these consistency conditions that we used in string theory to arrive at the same results. For instance, that's what I need to do. Let's look at the heterotic theory, for instance. Okay? In the heterotic theory, one of the conditions, the condition that was sort of really crucial in getting esoteric to, was the requirement of modular invariance. And if you remember our analysis, modular invariance played a really crucial role in determining the structure of the esoteric theory. Now, you might think, look, modular invariance seems like very different requirement from anomaly cancellations. Is it? And the answer is actually they're not so different. Why is that? You see, a string one-loop diagram is done over the fundamental loop. Now, that is the thing that makes all of string theory consistent. You know, it makes finite, it makes blah, blah, blah. However, you are allowed to do this integral over the fundamental domain only if you are fairly modular. Otherwise, it makes no sense. But if the theorem is not modular, then you did it only over the fundamental domain. But the whole thing is probably just inconsistent. But what do you get? You get effectively some sort of boundary terms at the boundary of the fundamental domain, at the very least. Now, if you remember our BRST analysis, our analysis for the decoupling of states that were BRST trivial. Okay? You might remember that operators that were BRST trivial that turned out to be that in order to show that they did not couple to other operators, we had to use the fact that something that was a total derivative of moduli space integrated. Now, if you pick up boundary terms by integrating over the fundamental domain, that will not be true anymore. The fundamental domain is a closed surface. If the theory is not modular invariant, this would not be true anymore. And so, things that were BRST trivial would not really decouple. Non-decoupling of BRST trivial states is essentially the hallmark of an anomaly. You know, in a gauge theory, the non-physical polarizations of the gauge boson would not decouple if the current were not concerned. If the theory were not gauge. These non-physical polarizations are BRST trivial. Okay? So the considerations that we used in string theory, though they sound different, are actually logically connected with considerations of anomalies. It's not as surprising as it may sound that, that imposing these string theory consistency requirements are also the same as the anomaly. Okay, so we're basically through. Let me quickly just